Hey, yesterday you heard me talk about like the overall mission requirements for the Mars mission, the Moon mission, some other things, and how it has to pay for itself. And tried to make the case for we have to be able to bring back a whole bunch of mass to help pay for things. And one of the challenges I mentioned back then was the power and energy required to do all this stuff. And if you're an aerospace guy and you play with airplanes, you realize that generally power is in the tens of kilowatts, maybe special application aircraft, you can get up to like low 1 to 3 megawatt type of stuff. But what I'm going to show you here is way beyond that. And we have to be careful that, when we start talking about the amount of energy and power we're needing, it's going to scare a lot of people who know the state of the art and or who know what standard is. So because we're way beyond that, it's going to scare the heck out of them. So we got to get used to large numbers. And like I said, it made the case that, for a real space economy, space settlement for the future, we need to really look at a 1 million kilogram a day, up and down, both ways. So you have that goal, made the case also rocket-based and reentry vehicles can't handle it. It's way too costly, and the timeline required to do all those missions is hundreds of years, and people are going to lose big time interest in it. It's also the cost, and it appears for right now, for what really makes the space elevator attractive is some sort of electrical solution. If you really look at stored energy systems, chemicals, all that kind of other stuff, we're just putting ourselves right back into what the rockets are doing. So it's going to be really some sort of an electric-based solution. But if it's a chemical laser or something like that pointing up there, that I'm just going to classify that as an electrical thing because you got to turn that into something. So electric power is a space for a single elevator, and I want to really look at if we're taking that overall mission of 20 years and what does it look like for an everyday type of thing? What's it look like to get 1 million kilograms up and down every day? And that's where I'm looking at this and saying, okay, well, what's it going to take to do that? And what kind of architectures are needed to fulfill that kind of mission or that kind of goal? Everybody loves equations when we talk about technology stuff. So when you look at vertical forces, you got gravitation, centrifugal, and you got the force balanced out. And what I'm starting to do is say that if you really look at throw the mass away, what you have is a gravitational equivalent acceleration. It really bugs me when people say, well, there's no gravity up there. Well, yes, there is. It's just that you're equalizing it out with centrifugal forces. So when you start looking at what is the gravitational equivalent acceleration, you start looking at the centrifugal force, the gravitational force. The red line is the equivalent. That's whatever you're doing on the tether is experiencing. So that's why I'm trying to coin a new way of thinking about gravity. It's really the equivalent acceleration that you're really talking about. And where they equal out is geosynchronous orbits. So anyways, that's a new thing for me. And you start looking at energy and power. You start looking at it, excuse me, vertical ascent, the energy required per whatever distance you're going up. And then you have the power required. You got to take into account the time it takes to do that. So then you have the accumulated, you integrated from the surface of the Earth. Oh, by the way, little nomenclature. I got the radius of the Earth plus the height above the surface of the Earth. That's what the H stands for, is the height above surface, not the radius. It's just how I defined it. That makes it simpler for people to understand. Okay, accumulated energy, you integrate over all that stuff, and accumulated power, same thing. Okay, so when you really look at it, what I was doing is I was targeting. Yesterday, I talked about the trade space is about 100,000 kilograms up to around 700,000. So I looked at it at this, 100,000 and specified that. And it's really a linear relationship. So if I wanted 700, I just multiply these numbers by 7. So when you really look at the amount of energy required to lift 100 kilograms 1 meter, at a specific altitude, this is the kind of energy you need to lift it for 1 meter, depending upon where you are in altitude. And this, of course, is in joules. So, and this is the accumulated energy when I really look at out what's the accumulated energy required. Now this, this is a big scary number. You're talking about gigajoules. However, remember, this takes days to get up there. So you got to take that gigajoules and spread it over days. So it really is not as scary as people think. But when you start seeing gigajoules of energy, it's going to scare a lot of people. But you got to think about the timeline that you're really doing this under and how does that look? But this is the overall energy. If you look at 100,000 kilograms, you're talking a little bit under 5 terajoules of energy required to get it up there. Now, of course, this is not taking into account inefficiencies in power electronics and a bunch of other stuff. That would be extra. Also, when you start looking at the power to raise that up, this again is 1 kilogram mass, 1 meter, based upon speed and altitude. And this is the amount of power you need depending upon, it's really dependent upon how fast you're going. And I was playing around with different mission segments, and I'll explain that. Why did I go from 100 kilometers an hour up to 1,000? Well, there's reasons for doing that. I'm more of a mission guy. I'm thinking in terms of missions is how do we get there? What are the things that customers are going to want to see, that kind of thing. But this is the power requirements again. As you can see below, 6,000 feet, you're talking about a lot of power, or not 6,000, 6,000 kilometers. There's a lot of power requirement. As you go up, it filters off. Here's the accumulated power required. Again, this is in the trillions of watts, but again, it happens over days. So you really have to go back. Whoops. Let's go back up one. So really, this is per meter. As you can see, it's like megawatts type of power type stuff, depending on how fast you're going to go. So again, I'm looking at trade spaces. What's the trade space we need to really be looking at? Again, this is total overall accumulated power to get to geo. And when you start looking at mission considerations, it's the time to reach to geo, the cargo and personnel required for ascent, energy and power, the technical and economic considerations for a single ascent descent. And then you have to look at what are the technical economic considerations for all the different missions. One thing I was playing around with is how do I get to geo fast? And if my limitation is the amount of power, let's say I'm using the basic ISEC concept of I'm projecting laser power up to a target. If I say, well, if I'm at sea level, I launch the thing, go 100 kilometers an hour up to 100,000 kilometers, and then I say, okay, now I'm out of the atmosphere, I'm going to take a constant power approach on target. So I think that's around 27 megawatts, if I remember right, somewhere around there. And what I'm going to do is I'm just going to take that 27 megawatts and I'm going to increase speed based upon that constant power. And this is the speeds that you can get to over on the thousands of miles, 1,000 kilometers an hour based upon altitude because of the fact that it doesn't take that much more to get this thing going faster. So this is your velocity curve depending upon constant power on target. I'm not saying you can make something go 70,000 kilometers an hour, but that's how much energy could be used to project it that fast. So we have to limit this thing. But that's just a different trade space as to how fast could we go. So I call this the max portfolio here. If I say I want to limit it, I know right now we're targeting somewhere like 100, 200, 300 kilometers an hour. But I was saying I want to get there faster. What if I limited it at 500 kilometers an hour or 1,000? Then how would that look? If you had that constant power curve, and then you say, okay, I'm clipping it at 500 kilometers an hour, and then up to 1,000 kilometers an hour. So that's how I was looking at this. It's like, how do I limit that? How do I clip that off? And are these doable? Well, it depends upon your point of view. I have some stuff that might be able to do this. So anyway, but it's not used in the current philosophy. Okay, if I start looking at the power required per meter based upon mission, if I look at the 200 continuous and the 300 continuous and not have the 100 and then constant power, then you need a lot more power down at lower altitudes than I think what's being currently used. And if you look at the power required, um, as soon as you get to top speed, then your power requirements drop off. Whether I'm going 500 kilometers an hour or 1,000 kilometers an hour to get up to geo. So these are kind of how your power usage looks depending upon do I use continuous speed? Do I do a gradual build-up type of thing until I get to a max limit and then drape her off? But this just kind of shows you that, and this is the max continuous. That's where I'm going up here. I'm going at 70,000 kilometers an hour. So anyways, this probably is not really doable, but I wanted to look at these different curves to determine what's this going to buy me as far as the overall mission. And what it does is it says, okay, if I do the max power thing and I use that constant power, then it says that I can get up there in about 2.5 days if I do that. If I go 1,000, if I clip it 1,000, I'm doing about 3 days. So going dangerous doesn't buy me that much more in time as far as getting to geo. If I do the 500 kilometer an hour clip, then it's going to take me, about 4 days to get, a little over 4 days to get there. The 300 and 200, it's a lot more time to get up to altitude. And to me, it's a matter of, well, if I have passengers and all that stuff, are they going to want to hang around for 7.5 days going 200 kilometers an hour? Or if I said, hey, I'm going to get you there in 3 to 4 days, that sounds a lot more attractive. So to me, it's a matter of, well, if we start talking about trade spaces and speed versus how quickly can I get there, I'm thinking, we want to be down in this area somewhere. That's just me. I think this is way too dangerous, but I'm thinking, well, 500 to 1,000 might be more attractive as far as getting stuff up to altitude a lot quicker. So again, like I said, I'm just looking at trade spaces to determine, how much power and energy do we need uh, to fulfill a certain mission within a certain time frame at a certain mass. And then we look at it the reverse. That's going up. Coming down, we look at the power required to re-enter space. Again, this gets back into kind of what Larry was talking about earlier is you got a lot of power you got to get rid of. And it's a matter of, well, if we look at constant velocity, then some of this power might be pretty hard to get rid of. And I think some of the other speakers also talked about different ways of dissipating power. So we might say, hey, down here, we're not going 1,000 miles an hour or 1,000 kilometers an hour. We got to do something different. So if you look at the accumulated power, same kind of curves, you got a lot of power coming down. And this is what I was starting to look at is if your power rejection is limited, then that's going to impact what your bring back velocity is going to be. So if you're looking if I can reject 1,000 or 50 million, I can come back a lot quicker. Uh, it depends upon how much power you can get rid of. And if I remember right, I think some of the people are targeting around 15 megawatts, if I remember right. So I was thinking this is the curve. So when you start dropping back down, even though I'm targeting a lot faster speeds bringing back, uh, they're down this area is where they are as far as flatline curve. But to me, it's a matter of bringing stuff back to Earth. You're going to have to start dropping in velocity depending upon how much power you can get rid of.
1 minute,
And
Stephen.
okay, and that this is just it's the same curve. It's just I'm starting at 8,000 just so you can see it a little bit better. But again, it's showing that hey, you got to start dropping off on velocity, that kind of thing. So if you're looking at the energy space level is dependent upon a lot of different things. And it's also looking at, hey, if I'm limiting in size, if I'm 100 kilowatt or 100 um, metric tons versus 700 metric tons, the power and energy is going to be different. But it means if I need to bring back 1 meg, then I need to start looking at how many vehicles do I need to do this. And if you really look at it, it's like, okay, if I start trading trade spaces of vehicle size, vehicle volume, power and energy type stuff to get that million kilograms a day back. And then it gets back into, okay, well, what architectures look promising for this? What new technologies we need to make this thing happen? And that'll define where we need to spend investment dollars and start looking at the science technology instead of just saying, what do we have available? It's a matter of what do we want to do? Well, how do we want to drive the boat? How do we want to drive that technology? Again, the down earth is challenging. Also, the inefficiencies is going to create a lot of waste heat, so that comes into the equation too. And we have to consider safety modes on the down earth. If there's a failure mode of some sort, what are those safety modes going to have to be? Uh, Again, you have to design it for a lot of different tonnage of precious metals, so it makes it attractive and new technology needs. All right, 1 minute's up.
Right, thanks. Questions?
Here's why. A couple of times I think you said that the safety is more of a concern for the down climbers than the up ones. I'm curious what makes you say that. I mean, I think either way, if you have a failure, by the time the climber gets to the ground, it's going to be coming down fast.
Well, I think on the up, you have more time to respond. If you have a failure mode, I'm talking about if your drive mechanism, your propulsion system doesn't work quite right, then you can engage some sort of friction brake to lock it in place. But if you're coming down and all of a sudden you notice I'm starting going faster and faster, it's like, whoops, you're going to have a bigger friction brake to make that thing stop.
I think you can
If,
actually use a friction brake because you can stop those rollers almost immediately and then rely on the mechanical impedance of the ribbon to slow you down gently. So I think the friction brake would work equally well in either direction.
Yes, but when you're going up, it will coast to a halt. Then you can apply the brake without too much problem.
But
yes.
I think the point is you can stop if you just clamp on that brake and like immediately stop your rollers, then you've got like the ribbon will immediately accelerate. It's got very little weight though, and so then it's going to be kind of a drag force that you get from the ribbon, which is equal to the mechanical impedance times however fast your climber is going. So I think the mechanical brake would actually work well in either directions. You don't have to engage it when you're stopped.
Blaze, does
Well,
that you be pulling the apex anchor down or stretching the tether or both?
You will be inserting a wave in the elevator, and yeah, it will end up, making it up to the apex anchor, which you're going to pull down a bit. And I think the main question is, yeah, you want to make sure that once you've dissipated that total impulse, the apex anchor isn't so low that it's going to come crashing down.
Yeah.
well, to me, all that stuff gets back into what are you preloading that whole tether as? If I have enough tension in that tether, am I really pulling down the apex anchor?
Well, I think this
Yeah.
is a constraint on the tension below the climber.
Well, if I'm not going into
Yeah.
compression below the tether, below the elevator, as long as I don't go into compression, then how am I going to bring that apex anchor down?
Agree. So I think we need to say we need to have at least this much tension below the
Right.
climber such that this particular failure scenario will not cause a
Right.
problem.
And to me that also and to me that's what the pretension is for, is the emergency modes where something's going out of control and I gotta lock it down or something like that, then
Mhm.
I don't try to deorbit anything. So if I have enough pretension in that tether, down at sea level, then it's all good.